On November 5th, 2018, a spacecraft launched in the same summer as the first Star Wars movie's theatrical run crossed a boundary at the edge of the sun's influence and, for the first time in human history, radioed back a direct, live measurement of what interstellar space actually feels like. Not an inference, not a delayed reconstruction pieced together months after the fact. An actual, in-the-moment reading, taken by an instrument that was still working, at the exact second it mattered most. That spacecraft was Voyager 2. And here's the detail that makes this story worth telling properly. Its identical twin, Voyager 1, had made the same crossing 6 years earlier. It couldn't do this. Voyager 1's equivalent instrument had already failed by the time it reached that boundary, forcing scientists to spend nearly a year piecing together indirect evidence before they could even confirm the older spacecraft had left the solar system at all. Voyager 2 didn't have that problem. And what its working instruments recorded in real time, at the true edge of our solar system, didn't just confirm what scientists expected. It broke several of their models outright, and NASA is still publishing papers about it today, nearly 8 years later. This is the real story of both crossings, why one told us so much more than the other, and what the difference between them actually revealed about the invisible bubble that surrounds our entire solar system. A story that doesn't need a single invented detail, because the true one already involves two identical spacecraft, experiencing the same fundamental milestone in two completely different ways, decades apart, at the very edge of what human engineering has ever reached. Voyager 1 and Voyager 2 were launched within about 2 weeks of each other in August and September of 1977, built as close to identical as engineering allows, each carrying 10 scientific instruments, and the now famous Golden Record, a phonograph disc encoded with sounds and images meant to represent Earth to anyone or anything that might one day find it. Despite the numbering, Voyager 2 actually launched first on August 20th, while Voyager 1 launched second on September 5th, but on a faster trajectory that let it overtake its twin and reach Jupiter and Saturn first, which is why the numbering ended up backward from launch order, a small quirk of orbital mechanics that's confused casual space fans for almost 50 years now. From there, their paths diverged in a way that would shape everything that followed, right up through the story this video is actually about. Voyager 1 flew past Jupiter and Saturn, and then, after a close study of Saturn's large moon Titan, was sent on a trajectory that shot it up and out of the plane of the solar system entirely, ending its planetary tour for good in order to prioritize that one specific scientific target. Voyager 2, launched onto a more patient and more ambitious trajectory, kept going. It used Saturn's gravity to redirect itself toward Uranus, reaching it in January 1986 after a 9-year journey, and then used Uranus's gravity to redirect itself again toward Neptune, arriving in August 1989, 12 years after launch. To this day, Voyager 2 remains the only spacecraft in human history to have ever visited either Uranus or Neptune, a distinction Voyager 1 never came close to sharing, since its own trajectory had already carried it away from the plane where those planets orbit, permanently ruling out any chance of a later detour. That's the first half of what makes this story's title true, and it's worth sitting with for a moment. Every piece of close-up data humanity has ever collected on 2 entire planets, their rings, their moons, their strange tilted magnetic fields, came from one single flyby each, decades ago, from a spacecraft that has never been matched or replaced since. But the more interesting half of that title concerns what happened much later, once both spacecraft had finished their planetary tours and kept drifting outward for decades afterward, chasing the same ultimate destination on entirely different timelines, the true boundary of the sun's domain. To understand why crossing that boundary matters, you need to understand what it actually separates. Our sun isn't just a source of light and heat. It constantly sheds a stream of charged particles called the solar wind, which blows outward in every direction at hundreds of kilometers per second, and inflates an enormous bubble around the entire solar system called the heliosphere. Inside that bubble, the environment is dominated by the sun, its particles, its magnetic field, its influence, stretching out far beyond the orbits of every planet, every dwarf planet, and the entire Kuiper Belt. But the solar wind doesn't blow forever. As it travels outward, it thins out and slows down, eventually running into the thin gas and cosmic rays that fill the space between stars, the interstellar medium, the leftover material drifting through the galaxy between star systems, far less dense than anything inside the heliosphere, but exerting its own steady pressure inward. The heliopause is the name for that specific boundary, the place where the outward pressure of the solar wind finally drops below the inward pressure of the surrounding galaxy, and the environment flips from belonging to the sun to belonging to interstellar space. It isn't a wall or a hard surface, but it is a real, physically measurable transition zone, one that theoretical models had described for decades before any spacecraft actually reached it. Crossing it means leaving the heliosphere behind entirely and becoming, for the first time, a genuinely interstellar object. not drifting through empty space between stars in the abstract sense, but actually swimming in the same diffuse plasma and magnetic field that fills the gaps between every star in the galaxy, including the very field lines and particles that our own sun formed out of billions of years ago. It's one of the most significant boundaries a human-made object could ever cross, and as of 2026, exactly 2 spacecraft in history have ever done it. No other nation's space program, and no other mission of any kind, has come remotely close. Voyager 1 reached that boundary first, in August 2012, at a distance of about 122 astronomical units from the Sun, roughly 18 billion kilometers, or about 122 times the distance between Earth and the Sun, a distance so vast that a radio signal traveling at the speed of light needs over 17 hours to cross it even today. There was just one serious problem. Voyager 1's plasma science instrument, the piece of hardware specifically designed to directly measure the density, temperature, and flow of charged particles around the spacecraft, had stopped reliably functioning decades earlier, not long after its final planetary encounter, and was eventually shut down for good in 2007, years before the spacecraft ever got anywhere near the heliopause. Without that instrument, scientists studying Voyager 1's approach to the heliopause were left triangulating an answer from indirect clues, the way a detective works a case from circumstantial evidence rather than a confession. Its cosmic ray detectors showed a sudden jump in high-energy particles arriving from outside the solar system. A strong hint, but not conclusive proof on its own, that the spacecraft had left the heliosphere. Its magnetometer showed the magnetic field strength increasing sharply, but strangely, its direction barely changed at all, which was itself a puzzling result nobody had fully predicted, and one that added confusion rather than clarity to the picture. If you truly left the sun's magnetic domain for the galaxies, many scientists expected the field's orientation to shift noticeably, not stay put while only its strength changed. For months, the Voyager science team genuinely didn't know for certain whether the spacecraft had actually crossed into interstellar space or whether it had simply entered some new, still solar region nobody had modeled before. The confirmation, when it finally came, was almost accidental. Nearly a year after the likely crossing, Voyager 1's plasma wave subsystem, a different instrument than the failed plasma science detector, designed to pick up oscillations in the surrounding charged particles rather than measure them directly, happened to detect a burst of plasma oscillations triggered by a solar eruption reaching the spacecraft's location. By analyzing the frequency of those oscillations, scientists could finally calculate the actual density of the plasma Voyager 1 was sitting in, using a well-established physical relationship between oscillation frequency and particle density, and that density matched what interstellar space, not the solar wind, was expected to look like. Only then, in September 2013, over a year after the actual crossing occurred, did NASA feel confident enough to formally announce that Voyager 1 had left the solar system. It was a genuine landmark scientific achievement, the first time any human-made object had reached interstellar space, but it had been confirmed backward, through inference and a lucky solar event, rather than through a direct, in-the-moment reading. 6 years later, on November 5th, 2018, at a slightly different location and a shorter distance of about 119 astronomical units, Voyager 2 crossed the same kind of boundary, closer to the Sun than Voyager 1's crossing point, a difference explained by the heliosphere's shape not being a perfect sphere and by the Sun's own activity level, shifting the boundary's exact location over the 6 years separating the two events. And this time, everything was different because Voyager 2's plasma science instrument was still working, exactly when the mission needed it most. The moment Voyager 2 crossed, its cosmic ray and low-energy charged particle instruments recorded a sharp decrease in solar particles alongside a simultaneous increase in cosmic rays from outside the heliosphere, the same signature Voyager 1 had shown, and the signature that, on its own, still wouldn't have been fully conclusive. But this time, scientists didn't have to wait for a lucky solar event to confirm what that signature meant, because the plasma instrument gave them the answer directly and immediately. A sudden, dramatic jump in electron density, by a factor of roughly 20, exactly the kind of sharp increase theoretical models had predicted should occur right at the true heliopause boundary based on decades of pressure. Balance calculations between the solar wind and the interstellar medium. NASA was able to confirm Voyager 2's arrival in interstellar space within about a month, not over a year, and confirm it with a direct measurement rather than an indirect reconstruction, a genuinely faster and cleaner scientific result than anyone had managed with Voyager 1. That distinction is the heart of what makes this story genuinely different from a simple repeat of Voyager 1's achievement. For the first time, humanity had two independent, direct confirmations of what interstellar plasma actually looks like immediately outside our solar system, gathered by instruments built to measure exactly that, rather than pieced together after the fact from a fortunate solar eruption. 5 separate research papers, each covering data from one of Voyager 2's operating science instruments, its magnetometer, its 2 energetic particle detectors, and its 2 plasma-related instruments, were published together in the journal Nature Astronomy in November 2019, giving the fullest, most direct picture ever assembled of what the edge of the solar system actually looks like from the inside of the crossing itself, rather than reconstructed months or years afterward. Here's where the rewrote everything part of this story earns its place, because Voyager 2's direct measurements didn't just confirm existing models. In several specific ways, they broke them and did so in front of a scientific community that, this time, had the instruments in place to actually notice. The first surprise involved the crossing itself. Voyager 1, in its final approach to the heliopause, had passed through what scientists described as 2 separate interstellar flux tubes that had somehow invaded the heliosheath, the turbulent outer layer of the heliosphere, acting as a kind of precursor disturbance before the true boundary, a complicating structure nobody had specifically predicted beforehand either. Voyager 2 found no equivalent precursor structures at all. Its crossing, according to the plasma instrument team, was comparatively sharp and direct, without the same complicated buildup Voyager 1 had experienced. 2 spacecraft, crossing conceptually the same boundary just 6 years and a modest distance apart, encountered meaningfully different terrain on the way there. A first clue that the heliopause wasn't the same simple uniform shell everywhere around the solar system. The second, and more genuinely strange, surprise came from just beyond the boundary itself. Voyager 2 detected a distinct layer sitting right at the edge of interstellar space where low-energy particles that clearly originated from inside the heliosphere were still streaming outward, escaping past the supposed boundary, at a location and in a fashion existing models simply hadn't predicted. According to the mission team at NASA's Jet Propulsion Laboratory, this behaved very differently from what happened at Voyager 1's crossing point 6 years earlier, where hardly any solar material leaked through at all. Scientists were direct about the implication. They didn't yet know exactly why this was happening, and existing models of this region of the solar system's boundary weren't able to explain it. That's not a small caveat. That's the mission's own science team stating on the record that a fundamental boundary they'd been modeling for decades behaved in a way their models hadn't anticipated, and that they only caught it because Voyager 2's instruments were working well enough to see the leak happening in the first place. There were smaller confirmations too, each meaningful in its own right. Voyager 2 directly measured that the plasma in nearby interstellar space is both significantly denser and noticeably colder than the plasma inside the heliosphere. Exactly what theory predicted, but now confirmed by direct measurement rather than indirect inference, closing a gap that had lingered since Voyager 1's more uncertain crossing. And its magnetic field instrument reproduced one of Voyager 1's strangest and most debated findings, that the magnetic field just beyond the heliopause runs parallel to the magnetic field inside it, rather than at some sharply different angle, as many models beforehand had expected. Seeing that same unusual parallel alignment show up independently at a second crossing point, measured by working instruments rather than partially reconstructed ones, transformed it from a possible anomaly of one spacecraft's data into a real, confirmed feature of how the sun's magnetic field interacts with the galaxies, one of the clearest examples in this entire story of a single result changing status, almost overnight, from curious outlier to established physics, purely because a second, better-equipped spacecraft happened to see the same thing. The surprises didn't stop once Voyager 2 settled into interstellar space either. Follow-up analysis, published in 2022 by researcher Leonard Berlanga and colleagues, tracked what Voyager 2 encountered in the years after its initial crossing, and found that the region just beyond the heliopause was far more dynamic than a simple, static, edge-of-the-bubble model would suggest. Voyager 2 recorded at least 2 major compression waves, and a distinct shock front passing through its location between 2018 and 2022, pressure disturbances rippling through the boundary layer of interstellar space itself, evidence that the region right outside the sun's influence isn't calm and static, but subject to its own weather, shaped by pressure waves propagating outward from solar activity even after they've crossed into interstellar territory. Interestingly, the shapes of these pressure fronts look different at Voyager 2's location than at Voyager 1's, smoother and more wave-like at Voyager 2, compared to sharper structures Voyager 1 had recorded, and researchers noted that Voyager 2 registered unusually high magnetic field strengths during its crossing, tentatively linked to its position in the solar system's southern hemisphere, where the surrounding plasma appears to be more compressed than in the north. Voyager 1, notably, never recorded a strong shock feature to match one of the clearest ones Voyager 2 did see, adding yet another asymmetry to the growing list. More recent modeling work, published in 2026, comparing both Voyager 1's and Voyager 2's full sets of boundary crossing data against the best current heliosphere simulations, found something researchers described bluntly as a well-known ongoing issue in the field: Reproducing Voyager 2's specific data has proven harder than reproducing Voyager 1's, with every current model underestimating how far out the heliopause boundary actually sat at the moment of Voyager 2's crossing, by anywhere from about 3.5 to 8.5 astronomical units, depending on which simulation and which set of boundary conditions researchers used. In plain terms, nearly 8 years after the crossing, and with 2 independent, fully instrumented datasets in hand, the scientific community's models of the heliosphere's true shape and behavior still haven't fully caught up to what the spacecraft actually measured. The heliosphere, it turns out, isn't a simple, symmetric bubble. It's lopsided, dynamic, and still not completely understood. And Voyager 2's working instruments are a large part of why we now know that with confidence, rather than merely suspecting it. Researchers working on these models have suggested the next step forward will likely require combining magneto-hydrodynamic simulations, which model plasma as a continuous fluid, with separate kinetic models of the neutral, uncharged atoms drifting through the same region. A more complex, computationally demanding approach that wasn't fully practical when the original heliosphere models were first built decades ago. Step back, and the full shape of this story becomes clear. Voyager 2 did 2 genuinely unique things across its nearly 50-year career that Voyager 1 never could. It remains the only spacecraft in history to have visited both Uranus and Neptune, giving humanity its only up-close data on either ice giant to this day. No follow-up mission to either planet has launched in the decades since, meaning every textbook image of Uranus's tilted, sideways magnetic field or Neptune's faint rings traces back to that single 1980s flyby. And every future mission concept aimed at either planet, several of which are currently being studied by NASA and the European Space Agency for launch sometime in the 2030s, still has to build its plans around data that's now approaching 40 years old. And decades later, at the far edge of the solar system, its still-functioning plasma instrument gave scientists their first direct, real-time confirmation of what interstellar space actually contains, a capability Voyager 1 had already lost by the time it needed it most. Neither of those achievements diminishes what Voyager 1 accomplished. Being first to reach interstellar space, even with an instrument down, even with a delayed and indirect confirmation, remains one of the most significant achievements in the history of space exploration, and Voyager 1 continues to hold the record as the most distant human-made object from Earth, a lead it's likely to keep for decades to come given its higher relative speed compared to its twin. But the comparison between the 2 crossings is exactly what makes this such a valuable scientific story. It shows, in the clearest possible terms, the difference between inferring a result after the fact and measuring it directly as it happens, and how much more a mission can teach us when both approaches are available to compare against each other, essentially turning 2 separate, decades-apart spacecraft crossings into something close to a real scientific experiment with a control and a variable, purely by accident of which instruments happened to still be working when each one arrived. It's worth pausing on just how unlikely that comparison was to even exist. Nobody designing either spacecraft in the early 1970s could have planned for this. The plasma instruments were built to study the solar wind near Jupiter, Saturn, Uranus, and Neptune, not to still be operating, if barely, decades later at the literal edge of the solar system. Their survival that long, on either spacecraft, was itself a minor engineering miracle given how far outside their original design lifetime both probes have operated. That one instrument failed early, and the other happened to survive just long enough wasn't planned by anyone. It was one of those accidents of hardware longevity that, purely by chance, turned into one of the more scientifically productive coincidences in the history of planetary exploration. 2 nearly identical experiments run decades apart, with one control variable neither engineering team could have controlled for on purpose. There's a quietly poignant coda to this whole story, and it's worth ending on. The very instrument that made Voyager 2's heliopause crossing so much more informative than its twins, the plasma science instrument that delivered that immediate, direct density reading back in November 2018, was itself switched off in late September 2024, not because it broke, but because NASA's engineers had to start making hard choices about which of the spacecraft's remaining instruments to power down in order to stretch its dwindling electrical supply. Both Voyager probes lose about 4 watts of power every year as their radioisotope generators steadily decay, down from roughly 470 watts each at launch, and mission managers have been shutting down one instrument after another on each spacecraft since the mid-2020s, specifically to keep at least something running into the 2030s. Voyager 1's cosmic ray subsystem went dark in February 2025, followed by Voyager 2's low-energy charged particle instrument the following month. Voyager 1 lost its own low-energy charged particle instrument in April 2026, though engineers left a small motor inside it, running on just half a watt of power, preserving a faint chance of reviving the instrument later if any spare power turns up. Voyager 2 is scheduled to lose its cosmic ray subsystem later this year, leaving each spacecraft down to just 2 functioning instruments apiece, a magnetometer and a plasma wave subsystem. The same secondary instrument that once had to stand in for Voyager 1's dead plasma detector all those years ago, and which will likely now be one of the last things still listening on both spacecraft, for whatever time they have left. Mission engineers aren't done trying to squeeze out more time either. Sometime in May or June of 2026, the team plans to test something they've nicknamed the Big Bang on Voyager 2 first, since it currently has slightly more spare power and sits closer to Earth, making it the safer of the two to experiment on. A coordinated swap of several of the spacecraft's older, power-hungry electrical components for newer, lower-power alternatives, all switched over at once in the hope of buying both probes still more operational years before the last instrument finally has to go dark for good. If it works, both Voyagers could keep transmitting at least some scientific data well into the 2030s, more than half a century after their launch, using instruments built with 1970s technology, sending signals that now each take nearly a full day to reach Earth in either direction. Neither Voyager is coming back, and neither will ever be replaced with anything as capable anytime soon. No mission currently planned by any space agency is built to repeat what either of them did, at either boundary they crossed. What they measured in November 2018, and everything scientists have kept extracting from that single, direct crossing in the years since, may be the most complete ground truth picture of the edge of our solar system that humanity gets for a very long time. That's what it actually means for a nearly 50-year-old machine to do something its own identical twin never could. Not a plot twist, not a threat, just an aging, humble instrument still working exactly when it needed to, telling us something true about the place where our sun's influence finally runs out. What do you think we'll learn once both Voyagers finally go silent for good? Let me know in the comments, and subscribe if you want to be here for the Big Bang power saving test NASA is running on Voyager 2 later this year.